Okay, so far we have seen the parameters related with the ADC and DAC. Now we'll start talking about digital to analog converters. Why we are starting with digital to analog? Because inside of the analog to digital converters, which we are going to see in the following sections, we actually have digital to analog converters. The principle over there is same, and we are using some of the components that we have got in digital to analog converters. That's why we start to investigate digital to analog converters. Okay, the question is, what does a digital to analog converter is doing? What is it doing actually? So analog to digital converters, by providing a discrete step or the quantized steps, because we can only make progress in these resolution like we have calculated in the previous examples. And in general, if you look at the conversion for the analog output, um, we are taking the range, okay, and we are taking the ratio of our digital input to our overall digital range, and we are actually multiplying two together. So this means that we are increasing the analog voltage or current at the output in proportion to its digital input over a digital range. And if there are any offset adjustments, we also do that. That's why we have got plus offset in that case. So sometimes we make the offset adjustment in these circuits in order to get a symmetric resolution around our bit setting. So for example, you do a bit setting number 1. So I can actually draw that. Bit setting number 1, which will give us a particular voltage step. Then we do bit setting number 2. That gives us another voltage step. Then we do another bit setting, which is number 3. That will give us another voltage step. And 4, and so forth, so on and so forth. Now, these are our inputs. And here, we are actually observing the output voltage change, right? So basically, if you look at the depending on what the real desired output is, you are getting this quantization error. That is, whenever you step up the analog output, you can only step up by this much. So you cannot step up anything less than that. Okay, so that's why we are using offsets over there. So in order to minimize the error, sometimes we put within this offset a resolution. So resolution divided by 2 offset. So whenever we receive a particular bit setting, we get a kind of mid-range value. And this will make sure that basically whatever errors we have is plus or minus all 3 resolutions instead of 0 and plus full resolution. So we are actually making the error symmetric around our outputs. That's why we use these offsets. So this is why we sometimes have an offset, and we already talked about in the conversions in our previous examples, and we also talked about the offset that may be coming from trying to minimize resolution error. And also sometimes we put offsets in order to calibrate the offsets in the circuits themselves. So that's why we have got this offset voltage and so on. Now, we have seen this formula. We have got the Vref, Vout, and so on, and we have used this in the previous example as well. And in general, just like we have a voltage output, it is possible to have a current output. So that's why we have got I out over here. So as you can see, I0 or V0, that's both acceptable. We can have them. And we can actually use the same exact equations as before. So we have, we can insert the voltage range. Now we are talking about the current range, and instead of voltage offset, maybe a current offset. So for example, if you wanted to figure out the offset value here, it will be I out over F multiplied by the digital values, which basically gives us the value that we are required for the analog output. Okay, so this is the basic idea or the main idea of the digital to analog converters. Now, another important thing in the analog digital to analog converters are the R2R ladder. Now, what is this circuitry? Maybe you might say that it's not related to our topic, but it's something important. It's the component inside of the digital to analog converters that is actually making this happening. Now, on the literature or on the market, you can find different types of digital to analog converters. But we actually choose this one because as this is going to be the most common implementation, which you may find in the microcontrollers and including our AVR actually. And it is popular because it can achieve a much higher degree of precision, and at the same time, this whole thing can be done with a single analog comparator. Okay, so you don't need extra components over there. We can just use a single analog comparator. Now, when we look at this circuitry, the first thing that you can easily spot over here is the analog amplifier with negative feedback. Now, because we can do it with a single one in this implementation, that's why it's so attractive to use this R2R ladder. Now, in order to understand the digital to analog converters, let's talk about how the circuit works. So you might need to remember some of your background from the amplifier circuits from basic electrical circuit theory course and how amplifiers behave when we put them in negative feedback modes. So you might need to revise those lectures in order to understand this. Now, it is clear that this circuit has a negative feedback. So because you see the output is tied through the resistor to the negative input of the amplifier. Now, for this discussion, we are going to assume basically that it's an ideal amplifier. Okay, so the first thing is we can assume that this is an ideal amplifier. So what do we know about ideal amplifier? If you do remember in the load analysis back in the circuit theory course. So if this is an ideal amplifier, what are some of the characteristics of the ideal amplifier? For example, what is the current that goes into the inputs over an ideal amplifier? So what is I plus, for example? Now, we can say that I plus or I minus, they're zero in ideal amplifier, if you do remember that. So this was one property of it. Now, what are the other properties for negative feedback? So for example, when we talk about the negative feedback ideal amplifier, what is the relationship between the plus input voltage and the minus input voltage? So this is one thing that we need to make sure that we understand. The way this amplifier behaves, for example, so let's assume that as soon as your V plus, so let's say Vi plus, starts increasing, okay? Now, what will happen? This Vi plus is actually going to increase with Vi minus. Okay, so VI minus will also increase. And then, if you remember, this amplifier is really amplifying the difference between VI plus, the positive terminal, and VI minus. Therefore, with the VI plus increases, the voltage at the output of the amplifier over here, it will also start increasing when the voltage at the output V0 of the amplifier. So we are actually basically increasing the voltage at the negative input, VI. So we are delivering current to keep increasing that until the two of the voltages are equal, and then the two voltages are basically at this output, it's going to be VI plus minus VI minus, it's going to be 0. So it will increase until it is 0. And then it will stop increasing the voltage. Now, if we decrease the voltage, the opposite happens. So basically, this amplifier will use its negative feedback until V plus is equals to V minus. So that will be an equilibrium or stable point. This is the property of ideal amplifier. Now again, in your circuit theory, you studied this negative feedback configurations with this very basic observations and very basic assumption. If those are the two rules, the input currents are 0 and the input voltages are equal to each other under the equilibrium. So we know the properties, we now understand the amplifier. Now, if we look at the positive input of this amplifier, for this part of it, in this DAC circuit topology, the positive side is actually tied to this ground. Okay? So that means that under equilibrium conditions, we are going to have negative side also settled at 0 volt. So this side also needs to be settled at 0 volts. In fact, because of that, often it's in this topology to be referred to as negative input or amplifier as a virtual ground over here. Okay, so this is actual ground, this is going to be a virtual ground. Because of the positive being same as negative input in negative feedback configuration, then the negative input is set to ground all the time to be equal to the positive input under the equilibrium. Okay, so now after those fundamental observations, we can go into the next step of analysis. Now, we make an observation that if this negative input is always 0 by tied to the virtual ground, then we can write an equation for this current around here going through that resistor. And that current is always going to be V0, V out divided by R2, which is equivalent to 2R. Or output voltage divided by 2R. We can say both, actually, which is also already stated over here, because R2 is equals to R. So then, that gives us a relationship between this current and the output voltage. And now we are going to establish another relationship for that current by doing KCL. If you do remember KCL. Now, like we have said before, current going in one direction has to be 0 because that's the input to the amplifier, okay? Which means whatever current comes into here has to go into the other direction as well, as long as there's any circuit for the current to flow, which is actually there. Now, basically, by KCL, the current is equal to the I in, I'll write it over here, I in will be equals to I out. Okay, so that's what's going to be used for the rest of these analysis. Now, notice we have got a the ladder structure, and the way this ladder structure on the negative input or the amplifier work is that in a particular topology, so that as you see over here, now if we consider these two resistors are in parallel, okay, sorry about my drawing. So these two resistors are in parallel. So the most effective resistance for the 2R in parallel and 2R, they are both 2Rs. It gives us the, assuming that the switch is closed, okay? Right now we have got 2R in parallel with 2R. So this is going to be like 1 over 2R plus 1 over 2R. So what was the result? Result is R. Now, R over here is in series with this R. So R and R, if you consider the fact that these are here also in parallel, when you think about it, R and R and then R. So if this switch is closed and it's also grounded, so what is this new circuit equivalent to? Or maybe what is this equivalent resistance in this circuitry? Now, this network is also going to be R. Again, we have got another one in series and in parallel with 2R. And that means that next level is going to be R as well. Okay? So this is R, and that one is R. Okay? So this is actually the reference voltage. We have basically 2R branching off in this direction, and 2 are always branching off in the other direction. So 2 are that way and 2 are that way. Okay? Now, this voltage over here, when it looks in this direction, is always going to observe R. This is why the current flowing out of VR has to be always VR over R, because we are going to observe R over here on all those points. Now that's the current. Now we have figured out the current, and now let's see what happens once we start asserting our digital inputs. Since this is a digital to analog converter, whenever we are asserting an input, we are going to be doing this by really flipping one of the switches. So if you think about, you're flipping that B0 to 1. Okay? So least significant bit is switching. Now, when we switch this one, the switch goes in this one direction. And notice that this current is going to change as a result of that switch. Now, why is that? Because this end of the resistor was connected to the ground, right? So now it's connected to virtual ground, because this was connected to ground. Now it's connected to the virtual ground. So nothing changed as far as the resistor is concerned. It moved from one ground, which is the actual ground, to the virtual ground. Now, that means the current here has not changed, and therefore the overall current has not changed. So this is actually the advantage of virtual ground, basically, because we are going from real ground to virtual ground that comes from negative feedback of amplifier, and the current does not change. Now, what does change, though, is that this current was flowing through this branch. So you can notice how we have got this current keeps splitting the current right, we get the total current. So VR over R over here. and then half goes into one direction, and this is 2R, and remember the other direction is also 2R. So the other half of the current goes through this direction, which is I over 2. Now, when it comes to branch, it splits into 2 again, and then to 4, and then it goes to I over to the power n minus 1, and so on in the direction. Okay, so it's branching down. Now, if we go back and flip the switch, so once we flip the switch, this I to the power n is now going to flow into the virtual ground, but it's also going to flow into this node. So now that means I over 2 to the power n is going to be equal to V out over R0, R2, sorry, not R0, R2, which is 2R, because we have got the current over here, and that current is actually V0 over 2R. So what we calculated before actually said negative of that, right? Because one of them is flowing in this direction, the other one is flowing in that direction, so it has to be negative. And the accumulation of the currents in the same direction is equal to 0. So if you move one of them to the other side, then you get a negative. So then this actually gives us, we can actually come up with a voltage in terms of VR and the resistor values. So if we rewrite the formula, we can get V out as minus I over 2n multiplied by R2, okay? Now this is my output voltage. Now I am going to get from this step, but remember I is equals VR over R at this part. So I can rewrite this as V0 or V out. I keep saying V0. It's going to be minus VR over R1 multiplied by R2 to the power n. Okay, so it's actually we are rewriting the formula, the same formula. Now, as we switch different switches, so if you want to change the bits over here, now we are actually sending more current into this node without changing the overall current because of the virtual ground and the real ground. And that means that as we send more current into this node, this current is going to balance it in order to match the KCL equation. So that means that the voltage is going to keep changing as I switch these branches. An overall formula then is going to be this formula over here that basically tells me or tells us that how the output voltage is going to change when each bit is going to be flipped in order to turn on these different switches to other direction. So now, as you can actually build the relationship between the reference voltage and output voltage by adjusting these resistors values, right now they are adjusted so that R2 is 2R1, and this is actually one way of implementing it, but it could be some other relationships as well. But this is an important relationship, and that's is going to give us our conversion in terms of one step at a time. Now, as you see over here, the least significant bit causes the smallest change. Therefore, it sets our resolution, like we have said it before. Now, the reason we introduced, as I already said, the digital to analog converters, we are going to see when you are trying to build an analog to digital component. Now, one of the components in there is a digital analog converter. So we need to have digital to analog converter inside of the analog to digital converter implementation. And this is why we introduce DAC first. And once we understand that big portion of the ADC could be easy to understand as well. Okay, so R2R ladder is actually the main building block of the DAC, and this is how it's working. Okay, if we move PWM for digital to analog function. Now, I'm not going to go into the details of the PWM because we are going to see that in the following chapters. But the PWM outputs can be used to generate these analog signals as well, in summarize, if you want to summarize it. And depending on the application, we actually extract these DC components by filtering out the high frequency components. So we can actually use a low pass filter over there, and we can easily generate a PWM analog signals. So that's all you need to know about this. As I said, we will talk about in more details later. Okay, so discrete DAC, this is actually one of the examples of the off-the-shelf component that you can find on the market so that you can purchase it and use it in your system. And it is also available in Proteus if you want to do some system simulations with them. And if we look the internals of some of these discrete components, basically it's the principle we talked about earlier. The way the range or spans works, the way the resolution works. In this case, for example, it has got an 8-bit digital to analog converter with 150 nanoseconds settling time. So that means we have to wait 150 nanoseconds to get a reliable output over there. And typically there's a DC bias circuitry in there, R2R ladder, current switching, and so on. And and that means there's a negative feedback amplifier, as I already described. So this is actually a discrete component that you can buy it and use it. And in this typical application over here, you can see that we can actually connect it with the external amplifier over here, okay, in order to generate different types of waveforms. As generally we can amplify the voltage. You may take the output as a current and convert it to voltage. This is what is actually doing over here. Because the output is current, so it's going to be converted to voltage by using the Ohm's law, and you can do any type of processing for the outputs. Now, when we talk about this type of processing, what we have tried to show in slide 7 over here, whenever we have got digital to analog converter, we may have some signal conditioning over here, so that we can drive the activator, because you might need this signal conditioning circuit in order to do some voltage manipulation, so maybe a voltage level shifting. So if this motor requires a particular amount of current, then you need to have a higher current, and then there may be a current amplification going on as part of the conditioning. So you can think about this as a driver that manipulates the output of the digital to analog converter to the requirements or the application on the actuator side. And we will have a similar conditioning circuit when we deal with the analog to digital converter as well, which I'm going to explain in a minute. In this case, moving in the opposite direction, basically processing the output of a sensor before the analog to digital converter can use it. Now, that was basically our discrete example. You can look at their datasheet to find more details about these discrete components and their accuracy and so on.